since we are learning on the parallel plate capacitor, so this parallel plate capacitor can be arranged in either the series or parallel connection, right? Series or parallel. So we look at what happens if we connect the capacitor in series. So C in series, and also C means the capacitors connected in capacitors in parallel. So this one is a capacitors in series. Capacitors in series. Okay, let's say I consider two capacitors connected in series, which is here simple capacitor C1 and C2 connected to a potential difference of V, or a battery or the voltage source of V. So this is C1 and C2. So for information, the charge stored in C1 and C2 is equal. Q1 here, charge stored in capacitor C1 is Q1, charge stored in capacitor Q2 is C2 is Q2, and the charge stored in both of them is actually the same if they are connected in series, right? And also if they are connected in series, so the total capacitance can be calculated by using this formula. 1 over C series is equal to 1 over C1 plus 1 over C2. However, the voltage across each of the capacitor, okay, let's say this is V1, this is V2, then V1 is equal to C2 over C1 plus C2 multiplied with voltage of V, where V is the potential difference applied to the circuit. V2 is equal to C1 over C1 plus C2 multiplied with V, right? So based on here, you can see that if this is 1, this one will be 2. If this is 2, this one will be 1, right? So these are the few important formula where the capacitors are connected in series. However, the capacitor connected in parallel. So I have two capacitors connected in parallel. Okay, let's say this is C1, this is C2, and connected to a potential difference of V. So since they are connected in parallel, therefore the voltages across each of the capacitor, V1 is here, V2 is here, because they are connected in parallel. V1 is equal to V2, which is equal to V, right? The C equivalent, the total capacitance where connected in parallel, is equal to C1 plus C2. And the charge stored in each of the capacitor, for example, in capacitor 1 is Q1, capacitor 2 is Q2. So the charge stored in the system is Q1 plus Q2, okay, where Q1 is equal to C1 over C1 plus C2 multiplied with Q. Q2 is equal to C2 divided by C1 plus C2 multiplied with Q. So if you observe it properly, this is 1, here will be 1, this is 2, here will be 2. Okay, so this is a formula for you to, important formula for the capacitor connected in parallel. And however, you have to bear in mind that these two equations is only valid for two capacitors only, which are connected in parallel, right? Same as these two equation also valid for two capacitors only. If more than two, then you cannot use this formula anymore. Okay, and now just now we was mentioned that this epsilon r. So epsilon r is basically called it as dielectric constant, right? So usually we'll add a dielectric in between the two parallel plate capacitor to increase the amount of charge can be stored in the capacitor, right? So then we have, if you insert a different insulator into the parallel plate, then it has a different value of dielectric constant, right? So what is the effect that you add the dielectric constant? So by adding dielectric, okay, so this dielectric means the insulator into the in between two parallel plate, the capacitance of the capacitor will increase, right? Because the epsilon r is more than 1. So with this dielectric, or with the insulator, the E net exists between the parallel plate capacitor, this parallel plate capacitor. If you insert the insulator in between the parallel plate, so the effect is the E net in between the plate will be reduced, right? So E net will be reduced. Okay, so by allowing, if E net reduced, so by allowing more charges to store for the same potential. Okay, what does it mean by this? So we refer to the equation. So the relation between the electric field and the electric potential is E equal to V over D. So where do I get this? You can refer back what you have learned before. Okay, this one. E equal to delta V over D. So we refer to the magnitude. So E equal to the magnitude is V over D. Therefore, V is equal to ED. Okay, V is equal to ED. E is equal to ED. So we come back to this equation. V is equal to ED, and therefore E is equal to V over D. right? E is equal to V over D. So by adding the dielectric in, so what happened here is the electric field will be reduced. So electric field reduced. Okay, so to maintain the V as constant, so V across the capacitor is constant, we do not change the battery. So according to Q equal to CV, so if E reduced, by right V will be reduced. So since the battery they connect to it is constant, so how can I increase back the electric potential? So the only way is by allowing more charge to store. And that's why by adding the dielectric into the capacitor, you are actually allowing more charges to store for the same potential. Okay, that means by adding the dielectric into the capacitor, more charge can be stored in the capacitor. Okay, that is the effect, that is the reason why you want to add dielectric into the parallel plate of the capacitor. Okay, now, so since we are discussing on the capacitor, so this capacitor can be charged or discharged, right? Capacitor can be charged or discharged. Okay, let's look at it. How can we charge a capacitor and discharge a capacitor? So by charging a capacitor, so charging a capacitor. So we need to connect a capacitor through a resistor to a potential difference of V, right? Okay, let's say the potential difference here is V naught. V naught means the maximum voltage that the capacitor can be charged to. So this one is R, this one is C. So which means this plate here will be charged to the negative plate, this plate below here will be charged to the positive plate, right? So by charging a capacitor, we need a potential difference of V naught and then connect a resistor series to C, right? This circuit, we will call it as RC circuit as well. RC series circuit, okay, to charge a capacitor. So let's look at the graph. When we charge a capacitor, Q versus time. So the charge stored in the capacitor will increase exponentially. And the voltage across the capacitor also increase exponentially, right? The current flow through the circuit will decrease exponentially in this way, right? So where this maximum value is Q naught, maximum value here is V naught, maximum value here is I naught. So the graph can be, we can use an expression to represent the graph where for the charge stored in the capacitor, Q is equal to Q naught, 1 minus exponential negative R negative T over RC, negative T over RC. Voltage stored across the capacitor, VC, has a similar expression. VC is equal to V naught, 1 minus exponential negative T over RC. However, for the current, so current flow in an RC circuit when the capacitor is charging is reduced exponentially, where the expression is I equal to I naught exponential negative T over RC. So RC here, we call it as the product of RC, we call it as time constant. Okay, time constant is the time taken for the capacitor to reach 63%. This is RC, to reach 63% of the maximum value of the charge, right? This one also to reach 63% of the maximum value of the voltage, right? However, when the current is reducing exponentially, so the RC is actually the time taken for the current to drop to 37% of the maximum current. Okay, so here is charging a capacitor. Okay, for discharging a capacitor, so we have to remove this battery, right? We have to remove the battery out from the RC series circuit if you want to discharge a capacitor. So discharging a capacitor, we use a capacitor connected to a resistor without any potential difference. Something like this. So initially, let's say the capacitance has been charged to the voltage of V naught, and the capacitance value here is C, resistance value here is R, and initially the capacitance has been charged to a charge of Q naught. Okay, now let's look at the variation of charge across the capacitor when it is discharging. So Q versus T. So initially the capacitor is fully charged, so it has the charge of Q naught and discharging exponentially until almost equal to 0, where the expression of its can be used, this expression to represent it. Q equal to Q naught exponential negative T over RC, So again, RC is the time for the charge to drop to 37% of the initial charge. So this is RC. However, the voltage across the capacitor also reducing exponentially. So here is VC. So VC means the voltage across the capacitor. Voltage across the capacitor will drop from the initial value of V0, reduce exponentially, and the expression is V equal to V0 exponential negative T over RC, where RC is a constant. That is the time for the voltage to drop to 37% of the maximum value. Similar to the current flow across the capacitor also will drop exponentially from the I0 value, and the expression is I equal to I0 exponential negative T over RC, where RC is the time taken for the current to drop to 37% of the maximum value. So this is the capacitor when it is discharging.